All right, so thank you, everybody, and good afternoon, good evening, good morning, depending on where you're logging on from. It's my pleasure to be here today with you all. My talk is going to be on efficient machine learning and a little bit on edge cloud trade-offs. So what I'll do is to start off with outlining some of the factors that motivate model efficiency and lean models. I'll then discuss some of the use cases where edge cloud trade-offs is something we need to deal with and the implications on model efficiency. I'll also be touching on some of the common, techniques that people employ for achieving model compression. I'll then talk, depending on time, I'll can touch on the AWS machine learning stack and specifically on Amazon Machine Learning Solutions Lab, which is where I'm right now. Like Richard said, that's where I'm leading a team and doing some interesting stuff. So time permitting, would be happy to share a little more about that as well. So let's take a step back and first of all, look at the history of AI and how it all came about. So AI, let me just step through these slides here. So AI, or the artificial intelligence term, is used to describe any system that can replicate any task that was previously done by human intelligence. And almost always there is, this is related to some kind of complex decision making where human judgment would be required. And most use cases for AI are looking at a probabilistic outcome. And this makes a prediction or a decision with a high degree of certainty, and just like a human judgment. And a very rudimentary form of AI is the rule-based system. So rule-based system is, like a subset of AI. And often rule-based systems are cumbersome to build, given that we need to factor in various permutations, combinations, and they're also prone to changes as and when the business requirements change. Rule-based approaches are not even an option many times, in just because of the size and the set of rules, or sometimes the decision-making logic is completely unknown, and that needs to be learned, and that's where machine learning comes into play. And almost all AI systems today are created using machine learning, and this uses large amounts of data to create and validate the decision logic, which is called a model. And the AI application then feeds the input data into that model, and the model outputs human-like decisions. So machine learning is like the underlying technology powering intelligent systems today. And in traditional machine learning systems, I guess a number of you are already very familiar with, given this is largely a tech audience, I heard. The traditional machine learning was largely centered on feature engineering, which is about identifying the right features that influence the decision making. And for that model to be effective, the input features need to be useful. And a lot of this depended on the domain knowledge of the modeler, and that played a huge role. But as time progressed, the number of features, the problems also started getting more and more complex. Potential features grow, identifying the right input features becomes a challenge. And which is where the question was, what if these features can be learned automatically? And such scenarios where there is a lot of unknown features, that's where a deep learning system really shines. So a deep learning system, you can say, is a type of machine learning that automatically learns the relevant features using what is called deep neural networks. And these systems have been, of course, motivated by the way the human brain works. And this lets AI system address fairly complex use cases that was not previously possible. So how does a deep learning system automatically learn the relevant features to solve a machine learning task? So the building block of a deep neural system is a deep neural network, and that consists of a network of simple interconnected nodes, and they learn simple features in the first layer of the net. And some of these nodes are activated. These activated nodes, input into the subsequent layers of the network. And in the following layers, it combines these features to derive more sophisticated features. And this process goes on until it computes the final output in the output layer. So neural networks was introduced back in 1943. And a question to all of you is, why is it that deep learning is becoming popular now. I don't know if there's a way to ask questions here in this platform, but if anybody wants to volunteer, and share your thoughts on why is it that it's been a recent wave for deep learning, would love to hear your insights. At the same time, I don't want to disrupt the screen sharing here, but I'm trying to switch back to the presenter screen here. Yeah, anybody who, if you feel free to put it on the chat, and it's great if it's interactive, and if you have any thoughts on why you think that the deep learning wave sort of caught on only recently, although the early thoughts of neural networks was proposed way back in 1943. I'll pause for a few seconds in case anybody wants to share their thoughts. All right, looks like
in the chat, Sushi.
Yeah, in the chat, or in the Q&A if they like. Just want to hear thoughts from the audience on why they think the deep neural network sort of wave caught on only recently, although the concepts have been around in the while, for a while.
Can you see the chat though, Sushi? Can you see?
I can. Oh, so I could see the Q. Oh, okay, got it. I see a lot of people writing. Sorry, I was looking at the Q&A.
That's why we're here.
Great answers there. Yeah, GPU, the ideas, absolutely, it's fashionable. Great, that's a lot of great perspectives there. So let me go into what I wanted to share here. So the adoption of neural networks was limited in the past, mainly due to two limiting factors. One is, you need large volumes of data to train deep neural networks, and data was limited back then. And second is the computing power required to train neural networks is massive, and access to this kind of compute infrastructure was not feasible back then. And with the recent advancements in big data and compute architectures like GPU, like someone in the audience shared, and cloud computing, these limitations are no longer an impediment. And here in this figure, we see some of the trends in big data since the year 2000. Firstly, computing power has increased 10,000 times since the year 2000, and the cost of storage of data has also gone down 3,000 times. And there has been an exponential growth of data created due to the rise of the internet, the smartphone revolution, and the social media. So data is ubiquitously available now, and these three ingredients sort of have made it conducive for deep learning to take off. And the recent advancements in deep learning, with all of that, we're seeing literally a tipping point where AI ML is creating breakthroughs and addressing use cases that create very measurable results, be it when customer experiences are being transformed with capabilities like conversational interfaces, personalization, recommendations, and business operations are being improved and sophisticated with forecasting, better decision-making through all the demand planning and so on. And then AI ML is helping companies create new products and services and business models to innovate and gain competitive advantage. So now let's a quick look at how some of the AWS customers are doing this. Intuit is one of our customers. They've built forecasting capabilities to predict call center demand on a particular day or time to make sure customer service agents are adequately staffed. And Convoy, another, it's a logistics company, is disrupting inefficient trucking by using deep learning to provide better matches for shippers and truckers and allowing them to move freight more efficiently. And in healthcare, Cerner is a very big American healthcare company. This is tapping into AWS's deep portfolio of AI services. And they are coming up with predictive care. So they've already developed a model that predicts congestive heart failure up to 15 months before the actual clinical manifestation. And likewise, there are great breakthroughs with NFL tapping into AWS's ML Stack. But the reason I'm putting these out here is, with all these, we are still just scratching the surface of the impact that AI can have across different industries and geographies. So why, while we have all these great benefits from the advances in deep learning, there are still many considerations when it comes to actually building up the deep learning models. Deep learning, I think I just shared that a little while ago, it requires significant amount of compute, memory, and power. And this has implications, firstly, on the cost of training your models. So by cost, I mean cost of infrastructure, storage, and even perhaps man hours to develop these models. And second, the large requirements of compute, memory, and power can become a bottleneck in conditions where we need real-time inference or to run the models on edge devices with limited compute resources. And lastly, and probably most importantly, aligned with the theme for today's talk, energy efficiency is a major concern for developing some of these deep learning models. A recent study published in the MIT Tech Review, it showed that just training a single AI model can emit as much carbon as 5 cars in their lifetime. So I guess the previous speaker also addressed some of these issues on reducing carbon footprint. And so it becomes very important in these scenarios how to think about model efficiency. I'll touch upon a few strategies that are used to achieve this model efficiency. So a larger model means more memory references and more energy. And one of the techniques that is used for achieving model efficiency is what we call model pruning. So pruning is a technique where we increase the model sparsity by zeroing out insignificant weights. And there are many different methods of identifying insignificant weights. And one example could be to use the L1 norm to determine insignificant weight groups. And prune models are generally easier to compress, and the zero weights can be skipped during inference. And this reduces the latency a lot. And these are, of course, because of the leanness, these are more suitable to run on the mobile and embedded devices compared to on cloud. I'm sorry, compared to the non-compressed full models. And pruning is one of the methods where for inference to efficiently produce models which are much smaller in size and more memory efficient and more power efficient. And like I said, they're also much faster with minimal loss in accuracy. Pruning is also, inspired by a biologically a concept called synaptic pruning. So in the human brain, some of the axons and the dendrites actually completely decay, which are less used, they decay over time, and these result in synapse elimination in many mammals. And pruning starts, from the time of birth and continues, into the mid-20s, even in humans. So it's a concept inspired from there. But how do we go about pruning? So if we could somehow rank the neurons in the neural network according to how much they contribute to the overall output signal, we could then remove the low-ranking neurons from the network, resulting in a smaller and faster network. And so this ranking can be according to an L1 norm or L2 norm of neuron weights. And after the pruning, the accuracy, of course, is expected to drop, and the network is usually trained, pruned, and in an iterative fashion for it to recover. Of course, if we prune too much at once, the network may be damaged a lot and unable to recover. But as a concept, so you're sort of removing the weights that do not contribute much to the model inference from the network, and this way you're kind of compressing the model. You move on to the next technique here. Quantization is another a fairly straightforward, simple technique that is often used, and this reduces the model size. We simply, reduce the precision of the model weights. A few different ways people, approach this is they look at converting the floats to integer representations, and just by replacing a 32-bit int with a 16-bit int, you can literally half your model size with quantization. We'll also touch upon a very interesting strategy called knowledge distillation. This refers to the idea of model compression by teaching a smaller network step by step exactly what to do by using a bigger network that is already trained. And so this bigger network is what we call as a teacher network, and the smaller network is what we call the student network. And there's two sets of labels here. One is the hard labels, which is, of course, the hard labels are the ground truth like you have in any other network. And what we also have here is a second set of labels called the soft labels. This is nothing but the output feature maps from the bigger network, which is fed in, in this diagram. I'm only showing it at the output layer, but you have these at every few layers, intermediate layers. You're having the output feature maps being fed in from the teacher network into the student network. And the highly complex teacher network is first trained separately using a complete data set. And this requires, of course, very high compute and all the computational resources. But once you have that, you then use that to train the smaller network. This is done such that the smaller network learns to mimic the exact behavior of the bigger network, and by trying to replicate the outputs at each of these intermediate layers. And so you're not just looking at the final loss, you also look at all the intermediate layers. And so they've recently, this is still being researched, and there's a lot of new modifications being suggested to this, interesting ones. And so instead of a single teacher, you have an ensemble of teachers, multiple teachers, and you also have a concept where you have a teaching assistant. So the teacher trains, an intermediate network called a teaching assistant network, and then the TA will in turn, train the student networks. And so, but this field is fairly young, and a lot of research still going on in this. I will now. Maybe after this segment, we can pause for any questions, but let me just move through a little quickly here. Would like to touch on some of the edge cloud trade-offs, and I'm picking this scenario of autonomous driving and the data collection that goes on as part of it, just as an example use case to throw some light on what sort of considerations you have with models when you're talking about whether to deploy them on the edge or on the cloud. So first, let me broadly explain sort of the scenario here. So typically, you have many of the big OEMs today. When I say OEM, the automotive manufacturing companies, whether it's Toyota, BMW, Nissan, or any company like that, they usually have their own fleets where connected car fleets, and these are collecting a lot of data. And typically the data, they collect data from different sensors. You're talking about, image, of course, a lot of them are collecting from the cameras and other sensor data that's being collected, GPS and odometry data and so on. So a number of this data which is collected, is sent to the cloud. And when it's sent to the cloud, of course, you can do a number of things there. You could look at packaging these and then sell to providers, those who are, consumers of this data. And folks like working on autonomous driving sort of use cases are very interested in consuming the data that's collected by this fleet of, vehicles. But a good consideration is that you do not want to upload every single data that's collected or every sample of data that's collected, simply because you're often interested in certain types of data and very specific aspects of data. So let me give you an example. So let's say you're interested in understanding or studying some of the urban road scenarios where, especially where it comes to dense pedestrian traffic, or you're interested to see how the vehicle interacts when there are, at upcoming stop signs or traffic lights. So what you want to do in such scenarios is to be very selective in the way you collect the data, and you don't want to be uploading all the data you collect over several thousands of miles from all these fleets, because that's going to have a huge impact on your cost, because your LTE bandwidth would be much higher, and also for the data set to be useful, you want certain types of data which are useful for your study, like the example I gave you. So often what they do in these cases is to actually have a trigger on the edge. So the data collecting sensors, let's say the camera is collecting the videos, this is usually coupled with a processing unit which resides on the edge, which detects a number of these objects and then uses that as a trigger to decide okay, here is a video segment that is useful for me, or here is a stop sign that I'm detecting, and that's going to give me useful data. And so that's often done on the edge. And the reason being that you can't afford to send every every second of data to the cloud and come back with an answer on whether or not it's also counterproductive, because the whole point is you want to do it on edge so that you decide even what to send to the cloud. So these models need to run on the trigger models, what I'm calling, need to run on the edge. And then, of course, the rest of the data is whatever you decide to upload to the cloud is sort of based on the outputs from these models. So that's about edge triggered data collection. And here, a lot of oftentimes the considerations people have here is the model needs to be lightweight, because this is typically running on an embedded device mounted as into the car as in a dash cam. So you need to be mindful that the model, in terms of even sometimes these dash cams get heated up because of multiple models running at the same time. So you need to be very aware of the size of the models that run on the edge here. So the other thing is, when you're looking at an edge cloud setup like this, one thing you can also do is have pairs of models that can work together and complement each other. Let me give you an example. So if you're looking at, let's take the same example that I just spoke to you about, just detecting pedestrians. So an object detector, a pedestrian object detector might be running on the edge, and that might be a very simple, basic model that is just, detecting, excuse me, just running out of power here. Just set this up. Okay, so so a very basic model, a naive model, could be running on the edge, and sometimes your requirements in terms of precision, recall, you could adjust these depending on if you're okay with just doing a crude a detection on edge. If your precision is low, let's say you're okay with that, but do a much more fine-grained or complex detection on the cloud, and these two can run as a pair. Maybe I'll give you another example to make it more clear. Let's say I want to do collision detection, and so I could run a simple model, which is, let's say I'm looking at, accelerometer and gyro and all of these information coming from the sensors, and I could build a very simple signal processing based trigger on the edge. So anytime I sense that something is like a heavy signal, including when the car runs in, let's say, into a pothole or a speed bump, it would still pick it up, and I'm okay. Because what I want to do is reduce, the data from that huge continuous driving data to at least potential areas which I think might contain the collision. And then on the cloud, I could run a much more sophisticated, detailed model, which might integrate, a camera modality and multiple other modalities to then give a more confirmed, indication of whether that was a collision or not. And so we could afford to play around with what you might run on the edge and on the cloud as a pair. And then let me go to one last thing I want to touch here. So in terms of the context, right? Sometimes you want to run multiple of these models on the edge, but it's possible that you don't need to run all of them, at the same time. Let's say you're looking at an application where you want to detect, scenarios, let's say pedestrians in this case, and sometimes you want to detect high speeding zones, and which is very relevant only to highways. So depending on the context, you could switch on or switch off the models depending on the context. And so you might want to then save your power on your on device by being selective about which model you choose to run. Simply based on the context of where the model is running, or you could use things like, if you're integrating this with the map information or various other ways where we could get in a simple signal to say, hey, this model is not even relevant here, so let's just switch it off and not run all at the same time. All right, so let me just pause here for a moment and see if we have questions that we want to take here. All right, so maybe I'll keep going, and towards the end, maybe Jessel, you could help me to select out questions, and then we could. Yeah, is there a question, Guy? Do I need to stop for any questions here? Just trying to look through here to see. Right. Yeah, some great comments and great call outs in the chat. I do see folks. Yeah, that's absolutely right. So although applications of deep learning networks to real problems have become ubiquitous, it will take time for people to start understanding as to how they're so effective. That's absolutely right. And Marcin, you brought out a comment on robustness. So absolutely, and I think that sort of feeds into how robust do you want it to be? Is a great question to ask in even deciding whether you want to run something on the edge or on the cloud. So if your requirement is that it's okay for it to be just a crude trigger, it's okay, I can compromise on robustness there, but I could do some post-processing on the cloud and improve the robustness there. So there are multiple ways to do this, and I think a lot depends on how well we understand the requirements of a problem, and oftentimes we are over engineering and we do not need something so fancy, and especially given the deep learning wave, we tend to sort of think about deep learning many times where sometimes a simple logic-based system would actually do the trick. And so I think we need to start questioning ourselves as to whether we really need what sort of robustness do we need for a particular problem? And I think working backward from there would be a great way to understand what to put on the edge and what to put on the cloud. Awesome. So let's keep going. I think I probably have another 10-15 minutes. So let me quickly move through this section here. So a little bit about our mission at AWS. So we've discussed different scenarios where you have edge cloud trade-offs and all that need to be made. And each use case is very different. Each use case is very unique. Like we spoke about robustness, and there could be various other factors that will influence how we tackle each use case, and the requirements are very different. And also the different enterprises have different levels of ML competencies and in-house expertises. And so the AWS ML Stack it offers a framework with different levels of or layers of abstraction with which we can build very customized ML solutions catering to the requirements of the use case and the customer. And so our mission at AWS is to put this powerful technology of ML in the hands of every developer, data scientist, and researcher. And we want to simplify machine learning and make it easy for developers to easily build intelligent solutions. Why AWS? So firstly, we provide a very broad and deep set of machine learning and AI services for your business. So we've launched over 250 new features and services in just the last year, and our pace is only accelerating. And second, we can accelerate the adoption of machine learning. So I'll touch a little bit on Amazon Sagemaker. So Sagemaker makes it much very easy for everyday developers and scientists to embrace machine learning. So I will walk you through some of the levels of automation we are able to get with Sagemaker in just a little bit. So before Sagemaker, doing machine learning was just very hard for many customers. And especially when you're looking at a very differentiated offering. So what AWS is doing is to invest in all the heavy lifting, and some of the things that differentiate you and your business is what you focus on, while we take care of some of those the heavy lifting in things that are very repeatable, which we can take on and onto the cloud. So I will get into some specifics in just a little bit. Let me, so here we've worked with tens of thousands of customers for moving their AWS and their machine learning workloads on AWS. And so let's look at the technology and the stack. So we have a 3-layered machine learning stack at AWS. And so we are innovating on behalf of customers to deliver the broadest and deepest set of machine learning capabilities for builders of all levels of expertise. And so at every layer of the stack, we're investing in removing the undifferentiated heavy lifting, like I just said, so that your teams can move faster and focus on what is differentiating you and your company. So let's walk through these 3 layers very quickly. So at the bottom layer is the frameworks and the infrastructure. So as for ML practitioners, at the framework level, you typically are looking at frameworks like TensorFlow, PyTorch, or MXNet, and TensorFlow has the most resonance and the largest community today, and we have a lot of TensorFlow expertise and experience inside of AWS, and 85% of the TensorFlow running on the cloud runs on AWS, and so we have dedicated teams that are working on building these frameworks so customers have the right tools. And we also have what is called the deep learning armies. So these are they're called deep learning AMIs. And so with this, you can quickly launch an Amazon, what we call an EC2 instance, which are pre-installed with all the popular frameworks, whether it's TensorFlow or PyTorch or MXNet or Gluon or Horoword. And so you are able to focus on building the custom AI models, and these come with already pre-installed packages at the lowest level. But let's say, okay, so let me also talk a little bit on the inference chip here, given that it's relevant for the edge stuff we spoke about. So Amazon introduced Inf1 instances last year. So these are based on AWS Inferential Chips. And so these are custom built by AWS for machine learning. Excuse me. And so the inferential chips are, coupled with some of the latest custom 2nd generation Intel processors. And, this gives very high throughput inference. And so they very high inference and also very low cost on the cloud. And a lot of the inference on cloud is, it's pay per use. So it works out very economically, for the customers. So you're able to achieve large scale machine learning inference for applications like image recognition, speech recognition, and so on, very effectively and cost effectively using the Inf1 chips. So the second layer in the stack is for those where you don't have not that many ML expertise, not that much of ML expertise in house, and let's say you don't, there aren't that many ML practitioners, and so if you want ML to be pervasive, you have to make it easy for everyday developers and data scientists to build, train, and tune models, and that's where the middle layer of the stack is, where you're not necessarily building everything from scratch. So let me. So let us understand a little bit about how the traditional ML development process worked before Sagemaker came about. So it's an iterative process. And so first, developers need to select the algorithm or the framework to build the model. Then they need to train the model on how to make predictions, and then you need to tune it to deliver the best possible predictions. And lastly, they need to integrate the model with their application, and then you need to deploy this into your system. And then complicating this development process are that many of the tools that developers normally take for granted when you build traditional software, whether it's debuggers or project management or collaboration and so forth, and these were all disconnected when it comes to ML development. So for example, while notebooks are great for an individual developer to build models, it's hard to share them with peers, right? And another example is model tuning, which sometimes takes weeks or, hopefully not months, but, days or even weeks, and a lot of tedious work. And typically to tune your model, you'll start with something random and iterate through several adjustments to see how the model changes. And this can be a very long process, a long cyclic process, and it requires you to adjust thousands of different combinations of your parameters. So because of the lack of an IDE or integrated solution, developers had to stitch together tools and workflows, and that's time consuming and many times error prone as well. So Amazon SageMaker is a fully managed service that removes that heavy lifting from each step of the machine learning process. And it brings a lot of tools together through an IDE, or integrated development environment. So you can test, debug, deploy, and even monitor and profile, and all of this in a single environment. And then since launch, AWS has regularly added many capabilities to SageMaker, and these have helped our developers build custom machine learning models. So you basically have that flexibility to build a custom model based on your requirements fairly quickly with SageMaker. I don't know if we have too much more time here. Let me quickly see if I can cover. I want to at least. Yeah, this is getting into more details about SageMaker. Maybe I'll skip this part, but some of the things that I like to let me see if I can touch on some things interesting here. So let me skip this slide here in the interest of time. I want to leave at least 10 minutes for a wrap up. So here's a slide that shows the different modules of SageMaker. So it has many features at each stage, starting from data preparation to model building to model tuning and deployment. One of the things our scientists really love is the model monitor. So this is used for automatically modeling model drifts. So if you, automatically monitoring model drifts. So if you, SageMaker model monitor, it continuously monitors the quality of the machine learning models in production, and it alerts you every time there's a deviation that you need to be watchful of in model quality. And this is a great way for scientists to know when it is time to retrain models, and models typically need to be retrained every few months. And so you automatically get insight on when you need to be coming in and retraining. So another nice feature is the automatic model tuning. So SageMaker can automatically tune your models by adjusting, thousands of different combinations of algorithm parameters to arrive at the most accurate predictions that the model is capable of producing. Just want to give you an example. This is a customer success story based on Amazon SageMaker. So NFL is an organization that has 3 terabytes of data with 1,500 hours of playtime per week. And so they've started collecting real-time player positions with the RFID tags and that are embedded in the shoulder pads of players and also in the game ball. And NFL collects large volumes of tracking data like XY positions every 10th of a second, speed, acceleration, distance traveled, and various such parameters. And so they were looking for a solution to sort of manage all this real-time data and get key insights from this for their fan engagement. And so NFL Next Gen Stats team, and that the stats team was actually very lean in terms of their own data scientists in-house, and so they were and not too many people who were trained in data science and so on. So they partnered with my team at Machine Learning Solutions Lab, and using SageMaker's all the built-in algorithms in the Jupyter Notebook. So we launched 20+ stats very quickly, and so the things like catch completion probability and all of that to keep the fans engaged, and it has helped the broadcasters with all their storytelling. Just thought I can show that to you as an example. So this was the architecture we built for them. So yeah, Gartner gave SageMaker the highest ranking amongst its peer group. Here, we'll spend a couple of minutes on the top of the stack. So this is for, we serve developers and companies who want to add, solution-oriented intelligence to their applications with just an API call. So they're not really interested in developing or not, well, let's rephrase it as they probably don't have either the resources or the and they want to move quickly and they want to deploy just with an API call rather than actually developing all these at their end. And so we have a lot of these ready services in these areas, from starting from vision to text and speech and chat bots and personalization, forecasting, and so on. I'll maybe just give a couple of examples here. So under text processing, so if you want to translate text to different languages, we have Amazon Translate. Or if you if you want to understand what's being said in those translated corpuses of text, so we have what is called Amazon Comprehend. And if you want to extract text from documents automatically from menu cards or from your prescriptions, whatever be the document or newspapers, we have what is called Amazon Text Track. And so all of these are built on NLP and deep learning. And then we have all the things that Amazon is relatively famous for, the chatbots with Lex, and we have personalization, we have forecasting. Maybe I'll just give you a quick example of recognition. So recognition can automate image and video analysis with ML. It's a service that applies machine learning to extract information from images and videos. And with no ML experience, and just by using a single API call, customers can add computer vision capabilities to their applications. So it's been used for media discovery and metadata tagging in live events, media libraries, social media, influencer marketing, and so on. It can detect who, what, and where in images. So you just need to, get Amazon recognition installed, and it's just an API call that automatically takes care of these things. It quickly identifies well-known people continually. It's updating that to make a set of public, celebrities who can be recognized. It automatically labels objects and concepts and scenes in your images. It provides, let's move here. Yeah, bounding boxes and yeah, so on. And then, another quick example here is Amazon Kendra, and this is for enterprise search. This is based on natural language query, because a lot of times keyword searches are not intuitive and they're very error prone. So workers have to learn keyword combinations instead of relying on natural language. So Amazon Kendra makes enterprise search easy by providing a deeper content analysis based on natural language understanding. So they, for example, when your laptop is broken, rather than having to remember the exact keywords to search, you can simply ask, where can I repair my laptop, and so on. So we have, customers here. This is a huge Korean company where they've been able to integrate Kendra into their systems very effectively. All right, so I think I'll just maybe take another 2-3 minutes to wrap up my presentation with the Machine Learning Solutions Lab. So while AI and machine learning technology is important to build successful machine learning initiatives, the organization culture is also important, and ensuring that you're ready to embrace transformation and that you have the skills in-house, or you can partner for where you need those complementary skills and expertise, and and then be able to get to speed with all the best practices and so on. And so AWS offers a number of trainings and acceleration programs, and we offer in-person trainings for both technical and business stakeholders, as well as free online training and certification programs for your developers. And we can conduct workshops to help you identify the best use case for your business and work hand in hand with your team to develop a proof of concept. And that's what Machine Learning Solutions Lab does. So we work closely with the customer to identify your business case of whatever is of highest business value to you, ideate together with you, understand what the data readiness looks like, and starting from identifying what that ML opportunity is, we work and what that ML success looks like for your organization. We work backwards with we have a team of very accomplished data scientists and a very capable team, which is very well versed in all these domains of computer vision and NLP, tabular data, and so on. So we work with the customer very collaboratively to roll out these POCs. And then we also work closely with the what we call a machine learning professional services team that will help to put what we build into production. So yeah, we also have programs like Deep Racer. Deep Racer is a fun fun thing where they actually sorry, I think I skipped a slide here. Yeah, so Deep Racer is you have your own, you can build your own deep racing car, and using all your machine learning knowledge. It's a very hands-on program that we have. I can maybe go to just the last slide on the lab here. So at my team at Machine Learning Solutions Lab caters to a number of different industry verticals, whether it is sports to automotive to healthcare, life sciences, or finance. So we work very closely with different kinds of enterprise customers, and like I said, starting from identifying what that ML opportunity is, we starting from ideation all the way to production. We work very closely with the customer, and part of what we do is also offering these knowledge transfer, knowledge sharing sessions, whether it's Sagemaker walkthroughs or together getting the customer very equipped with all the skills they need to be building very custom solutions that might meet their needs. All right. With this, I will come to the end of my talk today, and hope I didn't leave very little time for a wrap up and any other questions that you may all have.
Thanks, Suchi. I think that was a wonderful talk, I must say. And knowing your bias, and your background, I think it is just too good with the fields that you have worked on and the patents that you have. Definitely, people must have loved this talk because it tells right from the history of deep learning to what we have today on AWS and what are the trade-offs between edge and cloud. This is very important, how a little logic can do the trick, and why people are investing in different areas and whether they can decide between edge and cloud, I think. And I think the platforms that you have explained in detail that exist on AWS is going to be really marvelous for people who know little about machine learning or may have less resources to work on, but can get excellent results. And also the machine learning solution labs that your customers have been using. I'm sure people have enjoyed your talk, Suchi. And there is a question indeed from Neeraj in the chat session, if you could look and answer to Neeraj.
Sure.
Yeah.
With rising demand for real-time local data analysis, like from a myriad IoT sensors, do you think time to quickly retrain deep learning models on new info may not be sufficient to keep up with the pace of the data inflow? Yeah, that's a great question, Neeraj. I think, like I said, so I think depending on your requirements of your application, I think your question is more about, there's so much of data, and let me just make sure I understood your question correctly. So you're talking about retraining the deep models on new info may not be sufficient. So are you suggesting, given that the data is coming at such a fast pace, maybe your cadence for retraining needs to be that much higher to make sure you're catching up and incorporating any drifts that you may have because the data is coming up at such a fast pace, perhaps? So I guess the answer would really lie in terms of what you really want to do and the end use case, and what sort of how current you want to keep the model to make sure it is, if there are any drifts with the model based on new data. I guess retraining is inevitable, and the pace at which you do it or the cadence with which you do it is largely dependent on the application. So Neeraj, I don't know if I answered your question, but I hear you. There is it's a huge it's a myriad of IoT sensors, and in fact, the example I gave was just one example of the autonomous driving use case, right? So you think about in the wellness space with all the you have the wearables and constantly all your Fitbits and everything. You're capturing all your different metrics of your parameters in your day. There's just a ton of data that's getting collected from all these IoT sensors, and absolutely, it's a huge thing to keep up with.
Thanks, Suchi. I'll just hand over to Richard now to summarize the event, and thank you for such a great talk.